Good morning, everyone. Today we have Alice Pasetto. Alice studied at the University of Bologna and then obtained her PhD in Bonn at the MACS Institute for Astronomy. After that, she got a quantitative fellowship at the National Autonomous University of Mexico, where she is now assistant professor. And she's here with the Battiferro program, and we'll talk about magnetic field evolution in jets over here.
Hi, everyone. Hi, everybody. So yeah, thank you, Annalisa. And of course, I'm not going to make any magic today. And well, for those who do not know me or remember me, or why is not working? Well, here. Sorry. Okay. No. What is happening? I cannot move. Yeah, here. Oh my God. Yeah, but I cannot move the presentation.
You click on the slide.
Okay, so yeah, I will do that later. Okay, so I left, as Annalisa said, with a big smile in 2012, my alma mater, getting the degree of my master's degree, then moving to Max Planck Institute of Radio Astronomy and Radio Astronomy in Bonn, sorry. I got my PhD there in 2016, and now I'm in my new alma mater, the Universidad Nacional Autónoma de México. And yeah, for those, I'm sorry. For those who do not know UNAM is a very big institution in the country. It has this great goal to spread knowledge on all the country and North America and South America, and it has a lot of campus all over the country. And one of these, apart from Mexico City, the campus in Mexico City, which is a city in a city, there is another campus, big campus in Morelia, which is a UNESCO World Heritage Site. So if you haven't been there, I invite you, and please contact me so I can also give you a tour. The city is amazing. The food is super good and super tasty, and you can also drink a lot of good tequila and mezcal there. And this is just last slide before starting. This is the campus. It's like US big campus with a lot of green area. And this is pretty much all the staff working at the Institute of Radio Astronomy and Astrophysics. Okay, so my area of research is basically studying the formation and evolution of AGN jet, and with not only the continuum, analyzing the continuum synchrotron emission, but also its polarization, because it reveals, of course, complementary information. So I will give a brief introduction on AGN jet and spectropolarimetry. If you want to, please interrupt me and ask questions on the way. So briefly and very quickly, AGN jets are the system at the center of active galaxies. There are several constituents, and one of these is the jet, which are a relativistic electron moving in the presence of magnetic fields. So being such a structure, they are non-thermal radiation emitters. So since they emit synchrotron radiation, they are also linearly polarized. And to study the polarization property, we can do it studying the Stokes parameter, I, Q, U, and V, which are the results directly from the radio receiver of the radio telescopes. And applying this equation here, we can study polarization flux, the fractional polarization, which gives you an idea of how regular is the magnetic field, and the polarization angle, which gives you the configuration of the magnetic field. Then there are two effects which are very important also, very important in general and also for this talk, Faraday rotation and Faraday depolarization, which are altering the polarization properties here above mentioned. So Faraday rotation is the rotation of the polarized plane of an electromagnetic wave here when it passes through a magneto-ionic medium represented in this red circle. So the Faraday rotation, this change of the angle is linearly proportional to lambda square and the rotation measure, this Rm, the rotation measure, which contain indication of parameters of the medium, such as the thermal electron density, the direction, the parallel direction of the magnetic field, and the dimension of the magneto-ionic cloud. And interesting is also the sign of the rotation measure. Plus rotation measure meaning that the direction of the magnetic field is going towards the observer, and a minus sign is moving away from the observer. Then, yeah, now it's working. Then another is, the other effect is the Faraday depolarization, which is the reduction of the fractional polarization with wavelengths. And this is possible due to complex media configuration or magnetic field inhomogeneities within the object of study. And there are several scenario equations describing the depolarization, but basically there are two big families representing the depolarization events, and this is internal and external. In the internal case of depolarization, we have our jet, our synchrotron emitting source. We can think of it as composed by several layers, which are at the same time emitting and rotating the emission. And when the emission arrives towards the observer, it is depolarized. The external Faraday depolarization family equation is representing where we have our synchrotron emitting source. So the radiation passes through several media with different configuration of the magnetic field or turbulent magnetic field within it, and it depolarized. So basically what's happened here is that we can consider a jet at the same time as an emitting and rotating source. And what is happening is that the angle, the polarization angle, is not linear anymore with lambda square. So that equation of the rotation measure I showed you before, that is linear with lambda square, is not valid anymore, and the polarization decreased with lambda square. So the takeaway message here is that the Faraday effect alters the polarization property that I described before. How feasible is to perform polarization observation in AGN? Well, it's very challenging, basically because of these 2 points here, because polarization is just a small fraction of the total emission, and you need, therefore, high sensitivity observation. And since decades ago, we could only collect sparse and narrow band polarization data, so making difficult to follow very well the behavior of the polarization properties. But still, I mean, there are lots of very good work attempting and analyzing the very jet base in AGN jet. But to properly obtain physical parameters, we need to well sample both the continuum and the polarization spectrum. And this is now possible thanks to broadband receivers. Broadband receivers are now installed in the measure radio facility, present and future, like VLA, LOFAR, SKAO, and the new next generation very large array. And also with this bunch of broadband data, we also improve our ability to interpret this data using these two tools, which are Faraday rotation measure synthesis and the Stokes-Cooley fitting. And very briefly, what is Faraday Stokes-Cooley fitting? Sorry, is fitting of the both Stokes Q and U parameters using analytical models such as this one. So please focus on this panel in the middle plots in these images, which is the fractional polarization. So each of these equations represent a depolarization which are very different. Indeed, the external Faraday screen, as you can see, there is a sharp decrease of the fractional polarization, while instead the internal depolarization is characterized by this sinusoidal function, which is this sync function here. Okay, so now let's start with this story of an AGN jet. We will I will take you through a baby AGN jet with the case of the compact symmetric object, a mature AGN jet with the case of M87, and this reanimated, as I call AGN jet with a question mark, of course, the case of the radio relic MACS J0717, and I want to show you how through polarization we can infer some very good information on this topic. So let's start with the compact symmetric object. My student, yeah, now you cannot see her here. Vanessa Rodriguez, my master student, is leading this project. So just few introduction on the CSO. They represent a key phase in the life cycle of an AGN. They eventually evolve in FR1 and FR2 radio sources. And as you can see here from the coin survey, the morphology is very different. The CSO we comparing to a core jet. They are compact, symmetric, lobe dominated, and there are basically two scenarios which are trying to describe the nature of this class of object. The first is the frustrated scenario. So the jet are really confined into a very dense medium, and they are intrinsically young. And the depolarization modeling is going to help to discern which of the scenario is the most probable. And in particular, there is this engulfed cloud model proposed by Bigerman in '89, where it returns two features that we are looking in the radio data, and these are the internal Faraday depolarization in the polarized spectrum and a free absorption in the spectrum. So I got the observation for the largest sample of CSO from S to Ka band, so from 2 to 32 gigahertz of CSO with ATCA, VLA and ATCA. And as you can see here from these preliminary plots, so the targets show this GPS shape spectrum, so meaning that they are very compact, and most of them also show a break at high frequency. So thanks to this, we can also estimate the age of the synchrotron component, and roughly this is higher, actually, almost 20% of the sample, the source, show polarization in the spectra, and here is just the data as they are. There is no modeling applied to it. So we are now applying the modeling to see which of the two models, external or internal, is the most model better the data. So the catalog will be ready at the end of this year. Okay, so spectropolarimetric analysis here is helping us to understand the nature of a class of AGN object. So let's talk about M87. So for this experiment, what we wanted to do is to understand the characteristic of the magnetic field in an already formed AGN jet and how is the interaction with the surroundings. So AGN jet, the magnetic field characteristic of an AGN jet is the presence of a helical magnetic field. So we want to search for these features in a jet with polarization. So what we want to search for a rotation measure gradient, stratification of fractional polarization, and we want obviously to properly model the polarization property. Why the rotation measure gradient? Because if you have a jet, a resolved AGN jet, you want to see the sign of this rotation measure. So if the line are moving towards the observer and moving away the observer, this is a sign of this circular motion of the helical magnetic field. The certification of the fractional polarization is because you are searching for a higher fractional polarization at the edge of the jet where you don't have depolarization, while at the center the sum of the angle of the magnetic field cancel the emission. So at the center of the jet you expect low fractional polarization, instead at the edge high fractional polarization. So what do we need? We need to resolve the jet, so we need very high angular resolution transfer to the jet, high sensitivity, both the continuum and in polarization, to detect polarization, and high spectral sensitivity to perform the depolarization modeling. VLBI is the best technique to do such investigation. Still is very difficult because it explores, yes, a region very close to the central engine, but they cannot resolve the width. It's very difficult to resolve the width of that jet, and it collects sparse radio data because the receivers are narrowband. So VLA is another important instrument for such an investigation, and we are tracing different scales, but still we want to understand up to which scale the magnetic field is propagating, and plus the VLA has high sensitivity also for spectral analysis. So these are the beautiful images we have to deal with. This is M87 at observation between 4 to 18 gigahertz. You can see that we could recover also extended emission of the jet, and this is the highest angular resolution image of the jet, and you can see already that the jet in its 2 kiloparsec length has a lot of substructures from the HST1 till the edge of the jet. And this is the beautiful image of the fractional polarization of M87 with in yellow strong fractional polarization, high fractional polarization, and the blue dark are area where depolarization is occurring, and the green line are the magnetic field line in the jet. So you can see that it swings very much and it follows very well the morphology of the jet. So now I concentrate, in the other results are concentrated in the conical jet part. So again, zooming in the first, this is the first kiloparsec of the jet. You see a lot of substructure. We could identify these 2 filaments, which are moving as a double helix in this conical jet part, and the polarization is following pretty well the morphology, the total intensity morphology, and especially in this area, we could detect large fractional polarization where the 2 filaments separate very well, and low fractional polarization where the medium is much more complex. Plus, we obviously we produce a rotation measure sign map to all the jet of M87, and in this part we could detect a clear gradient of the sign of the rotation measure. In red, the line are moving away from the observer, and blue is moving towards the observer. So this is a clear sign of the presence of a helical magnetic field. We also perform depolarization modeling in these 2 areas marked with a white circle, and the modeling also is suggesting an internal depolarization modeling. So all the changes in polarization are intrinsic to the jet itself. So we have found the stratification of the fractional polarization, rotation measure gradient, and the polarization are intrinsic. So we detect for the first time, rotation helical magnetic field up to 1 kiloparsec. So we also ask why the helical magnetic field is maintained to such distance from the black hole. So the answer is that there is a synergy among the presence of a helical magnetic field and the plasma instability of Kelvin-Helmholtz in the jet that are feeding each other. Okay, so spectropolarimetric analysis here in this experiment helped us to produce a 3D map of the magnetic field configuration and study the interaction of with the medium. So now the last part, reanimating a GNJ, the case of the relics MACS J0717. This is another, was and is matter of topic for the master thesis of my student Omar Vilchis. So radio relic are these giant megaparsec synchrotron emitting source, which are tracing shock fronts in a merging cluster, and there is a debate in the community whether these structures are electrons accelerating in thermal ISM or a sample of fossil electrons previously injected by an AGN jet and re-accelerated by shock. So polarization will also help infer which is the nature of these electrons. So these are the images, total intensity, continuum, and polarization at 10 gigahertz, so quite high frequency for such an object of the radio relic. As you can see, the morphology is very complex. Here, the NAT, the narrow angle tail, is the AGN of the radio relic. And just to help the eyes here, in pink are the region where shock fronts are supposed to be present in the relic. And in the red are the region where we analyzed the polarization properties. So this is the map of the fraction of the polarization intensity map with the line of the magnetic field, which are following the complexity of the continuum. So we took this 10 gigahertz data and we performed Stokes QU fitting, adding also other data available in literature, especially at C and S band in polarization. So we applied several depolarization modeling and nothing fits. So you can see for all the region we consider the data do not fit properly with the low frequency data. So something is happening here. So probably the low frequency data are tracing a different medium with respect to the high frequency data. So we took the high frequency and we perform a Stokes QU fitting alone, and the data are suggesting indeed an internal depolarization effect. You can see that there is a quite increasing of the fractional polarization along the area where the shock fronts are, and there are also indications of changes in the rotation measure sign, meaning that there is some rotation of the magnetic field. And just to finish, we got new observation, VLA observation at high frequency, deep observation at X band, 10 gigahertz, so the same frequency as this work, and also Ka band, 15 gigahertz. So we want to use all this new observation to make a proper study of the depolarization mechanism in MACS 0717. And so yeah, this is the takeaway message for this kind of study. So it is helping us to understand the particle acceleration mechanism. And with this, I finish and I take questions. Thank you. On time.
Yes. Are there questions for the speaker? Yes.
How did you select the CSO sample?
Oof. Oh my God. It was a long time ago, but so now I try to remember. Well, it was selected from morphology map with VLBI study. It was the coin survey of 2000. Some of them are also unpolarized point-like source from the VLA calibration source. There are other group here at IRIA that work a lot with CSOs, so I also take those samples. So the details now I don't remember, but yeah, and also obviously I select those that at the resolution of the VLA had to be obviously compact. Still, in our data, there are very few that are marginally resolved at the resolution of the VLA. So those targets will be treated with in a special way, of course, with self-calibration. And also the flags. Now I don't remember which was the cut in the flags. But yeah, it was here's a
Yes. In Austrian, you showed this beautiful image of M87 with the head structure, and this idea of having the Kelvin-Helmholtz instability, let's say, supporting somehow the structure of the parsec scales. So does this did you test this model only on polarized data? Did you use complementary data to support?
So there is in literature already a very nice work by Lovanov in 2005, if I remember well, where they study the instability, Kelvin-Helmholtz instability, studying the oscillation mode, the lambda mode propagation, and they already mentioned that. So to test this scenario, we also calculate the energetic of the jet up to this scale. And if you want, I can show you. And well, is on. And yeah, but anyway, so yeah, we also study the energetic of the jet, and we see that this particle dominated the jet up to this scale, so it's supporting the instability, the propagation instability of Kelvin-Helmholtz up to this this
combination of total intensity and polarization.
Yes.
Thank you.
You think it's imaginable, even in the far future, to look for helicity in diffuse radio emissions, like in relics? What are the requirements? So to test if there is any helicity there.
This will be very, very interesting, and of course, with the new instrumentation, will be easily addressed. I think with
easily addressed.
See, yeah, especially with the with also SKA, but you need also to. The importance of this study here of the MACS 07, now I cannot anymore. So the importance of this study is that we are detecting this structure in polarization at relatively high frequency. And this high frequency in radio are tracing, we are looking very close to the shock front regions. So with the ngVLA, which will be sensitive towards band 1 in ALMA almost, I think, right, Charlie? No, band 3.
100.
Okay, 100 gigahertz. And it will have a very high sensitivity. All this structure will be easily followed among the frequency bands. So I think that the depolarization modeling will be very powerful.
Resolution is not going to be an issue. You will have enough resolution to look for this corkscrew sort of.
Yes, of course.
Okay.
Yeah, because it will have resolution. You will have the resolution you want with this new instrumentation. So it will be very easy to address all these questions.
Because ideally, if all jets have the same helicity, then that helicity, if this jet is feeding, yeah, should be somewhere also.
Should be here. You should have trace. So I mean, if this is true, the scenario is that the jet ejected a long time ago non-thermal electrons. They propagate in the medium. then the shock reaccelerates some that is already mildly relativistic. So intrinsically, they are non-thermal electrons, and the property that you see here, you should see also in the other substructural region along the relic. Now it's very difficult because there is a technical issue of the sensitivity and resolution of the telescope, but in the near future will be easily addressed. For example, ngVLA will be 10 times more sensitive and 10 times higher angular resolution of the VLA at the present day.
Is the ngVLA fully found? I mean, is it going to? I don't know the situation.
This is a political situation. Yeah, from what I know, the ngVLA is founded till next year. No. I mean, no. Yeah, it will be founded. But it's critical with the Trump administration. There are a lot of cuts, and they are suffering quite a lot with the present administration. But UNAM is supporting, and UNAM is one of the official partner of the ngVLA, and we are renovating the agreement with NRO at the end of this year, and with the hope that everything will be smooth for the next years.
Any more questions? Yes.
The question, yeah. Excellent on the talk. Can you go back to the general MACS?
Yeah.
So I just probably missed this, but why do we observe larger fractional polarization when the two jets are, let's say, too many?
Okay. Yeah. Okay. Yeah. So if you see here, so this is a cut. Okay, following this, the two filaments, the pink and red filaments in the total intensity. So this is the cut of the two filaments between node E and F. So it's this area, okay? And you see that the fractional polarization, especially in this part, by chance, because it's really parallel to our line of sight, we could see an increase of the fractional polarization and a gradient of the rotation measure. But we have seen also a gradient of rotation measure, which is this panel here, in node E and node CF. Is not visible, as you can see, this structure also in the fractional polarization in the map, because the jet is moving. Okay, so you need to have a jet which is really parallel to your line of sight to see these features. Now, why you see large fractional polarization? Well, because you have at the edge of the jet, you have just one direction of the magnetic field carrying a fractional polarization. So you have a concentration of magnetic field line with just one value of fractional polarization. So you have X fractional polarization. In the middle, or if you have a complex movement or a preferred, if you prefer to see, if you have a preferred direction of the jet, you have just one fractional polarization that you receive, that the observer receives, because polarization is just summing a lot of vectors. So if you, in the center here, if you sum the vector, they cancel out. Okay, so you expect in an ideal jet to have higher fractional polarization at the edge, because you have just one preferred direction, and zero in the middle, because the vector cancel out in the middle, because you have the helical motion is a composition of a linear direction and a circular motion. Okay, so that's why you expect this feature.
We have more ordered magnetic
field. Indeed, yeah.
Polarization.
Yeah, here, indeed, you have a very well-ordered magnetic field. And if you see here, the magnetic fields in this part, the lines open like a funnel. And you have a preferential direction and a compression here and here, enhancing making visible and higher the fractional polarization.
Okay, that was the final talk of the season.
Thanks.
And then